So we started with the metric space. We started with a set and a distance function d, which is a metric function on this. Using this, we define what is called a topology on X. Topology means it is just a collection of sets satisfying something, satisfying some property. Arbitrary union is there, finite intersection is there, empty set is there, whole set is there. So this is just a collection of, this is our collection of open sets. See, you can take any set and discuss and declare a collection of set as topology provided it satisfies some condition. That's called a topology on a general set. It need not come from a metric. But when we have a metric, then we can take the collection of open set, it satisfies this property, and that is a topology on that. So we defined this open set using open balls. Okay? So for example, if you take Rn or Cn for Rn for our convenience, on this we may have different metric. For example, we have defined d1, d2, d infinity. You can define dp for p between 0 to 1. But I mean, if you want to complicate it, you can do that. But they all give the same open set here. Okay. Reason? Is there a reason for it? You say yes. Equivalent norm you can prove. We haven't proved it yet. Okay. So for example, if you take the open, for example, if you take R2, okay, a open ball in D1, for example, D1, okay, you want to consider a open ball around some point here, but any open ball here will be a translate of this. If you have an open ball here, you can B of, this is a property of any normed vector space, normed linear space. If you have a normed linear space, then that is just B of 0R. Okay? This is just property of any normed linear space. In fact, what is called a locally convex space or something. I mean, this is the property of that. Okay? Property is any open ball anywhere B of XR is just X plus means all those elements X plus something X plus Y here. This is a set. This is an element. Okay. This is a set. X plus A plus B is a set. If you have two set, you can define A plus B. A set of all A, I mean, this is of course possible only in a linear space. All those small a plus small b, where A comes from here, B comes from here. Or if it is just one element, it is just X plus Y, where Y comes from here. So any open ball BXR is X plus B0R. Okay. That's right. This is also, that's also non-linear space, R times B01 or something. So it's enough to look at B01. So how B01 looks for this? So in D1, B01, it is just all those XY such that that norm is less than 1, which is just mod X plus mod Y is less than 1. Okay. And it is just plus or minus here, plus or minus here. Mod is there, plus or minus here, plus or minus here. Okay. I mean, satisfies this property. So it is just X plus Y equal to 1 is this line. And there are other things which are this line. So, I mean, you have to exclude the line. The region inside this is the open ball. Okay. In D1 norm. D2 norm, you know, that is just the circle. Okay. X square plus Y square is less than 1. It is just the disk, open disk. Okay. I don't have to write. On the other hand, in D infinity norm, D infinity metric, the open ball is all those XY such that, I mean, the B01, B01. As he said, it's enough to look at B01, then any B0R, R times B01, and you can translate it to get all open ball. That is going to look like, I mean, it's just the maximum is less than or equal to 1. So it is just mod S less than 1, mod Y less than 1. If you put plus or minus or something, then that is just going to be, if you just look at it, that is just going to be something like this, where this is 1, 1, this is minus 1, 1, I mean, those coordinates. Okay, so it's clear. But you can see that if we have a ball here, then you can get something here like this, an open ball, something less than this, or you can get something like this. Okay, so and you can get, of course, a ball inside this. Okay, if you want. So if you have any open ball in one metric, you have a ball in another metric. That is one way of doing it. But to prove it mathematically, you have to work it. Okay, to prove it mathematically, you have to choose R and work it out. It's easier to work with closed sets. For example, we have got any polygon. Say it again. We got
Here we got a square and
yeah
we got a circle.
yeah
Balls and a different metric.
different metrics. Yeah,
Can we find a metric so that we can get a pentagon or a
I don't. I haven't thought about it. I don't. I mean, we have DP and all that. Pentagon and all, I'm not sure. I don't think so. You can think about it. You can come up with this. Okay? But the point is, two metric gives the same open set if they give the same closed set. Okay? To say they have give the same closed set, it's enough to prove convergence in one metric is equivalent to convergence in the other metric. So convergence in D1, D2, or even the DP or whatever, D infinity is equivalent to saying pointwise convergence. This is true for all of them. So they are all equal. So they give the same closed set. So they give the same open set. Okay? If some xn bar converges to x bar, where xn equal to x, I mean the coordinate. I mean pointwise means coordinate-wise convergence. Maybe I write convergence in this coordinate-wise convergence. Okay. So because of that, they give the same closed set. So they give the same open sets. Okay. On the other hand, I mean, you have xn, which is a sequence, which has coordinate xn1, xn2 up to xn. And this is converged to x bar, which is another x1 up to xn. So x1, n1 converges to x1, xn2 converges to coordinate-wise convergence. That is clear because you write it down, no? This some convergence in, I mean, convergence, you write xn bar equal to xn1 up to xnk. Maybe rk, okay? I mean, this n is sequence n, and that is the coordinate. Or let's call this k, and this is n, okay? And this converges to x bar, which is equal to x1 up to xn. Okay? This convergence means what? Some in L1 metric summation x n is in the bottom minus x1 goes to 0 as n goes to infinity. So each of them should have, they have to go. On the other hand, if each coordinate converges, then this converges because the sum is finite because of that. And this doesn't work in L1. Okay? I mean capital. I mean L1 for sequences, L1 sequences. On the other hand, L1n and L2n, the convergence is not just different. I mean, they are completely different spaces. L1n is contained in L2n, but they are not equal, of course. Okay, 1 by n is here, 1 by n is not there. Okay? But anything here will be here. This is because when something is smaller than 1, then the square is less than that, right? If xn is something here, okay, xn is in L1, okay, then xn square is less than xn, okay, for mod xn less than 1, right? So if this converges less than infinity, then this converges. Okay? Okay? So that's why small L1 is contained in small L2.
That with respect to that, every ball is like with respect to any other metric, the balls are contained. The ball we got with metric. For example, let me say the T1 metric is there, such that we got a ball T1.
Yeah.
Now, with respect to metric D1, can we say this ball B1 will contain all other balls with respect to any another metric?
Any norm will work because as I said, norms are equivalent, no? No, as far as the norm is metric is given by a norm, any two balls are equivalent. It will contain another ball. That is to prove that two norms are equivalent, which you seem to have seen the proof. If not, we will prove it again. Okay, so from that it will follow. If it comes from a norm, a metric need not come from a norm. For example, discrete metric does not come from a norm, and there are other metrics. So and there are topology which need not come from a metric. So there things are different.
There is a larger ball always contains every other.
That's what I'm saying. If you have one metric, it will contain all the other things which comes from a norm, right? Sorry. I put it in the silent mode somehow. Sorry. See, if it comes from a norm, then all the metrics are equivalent. So one ball will contain all the other ball. That's all. What is? If something is in L1, L1 of n is all sequences which are summable. We L1 of n is all those sequences. It is just the infinite version of this. That's all. Xn such that summation mod xn is less than infinity. Okay. And L2 means it is just the square. L infinity is all bounded sequences. Okay, we defined last time. Okay. So all those, so L1 is contained in L2, contained in L infinity. Okay. Of course, all bounded sequences need not be summable, and all if it is summable with, if it is summable, then it is square summable. Otherwise, not true. 1 by n is square summable, but it's not true, and all bounded sequences need not be something like. So natural number. N is natural number. Sequences, it is just a function. It is just a that is just L1 of finite set. What we have, L1 of any set, you can a finite set is you can write it like that. Here the set is n. You can just call it L1 if you want. No problem. Okay. Yeah, that is for indexing. You can have L1 of Z if you want to. No. Xn is this index is n equal to 1 to infinity. This is n equal to 1 to infinity. Right? Xn is in complex number or real number. It's a vector space. That I cannot lean. Thank you. I am not supposed to lean down. Okay. It's a vector space over complex number, real numbers, depends upon what kind of sequence you take. Okay. So here coordinate convergence need not imply, here the coordinate convergence means each entry converges, right? If you have a sequence, xn bar equal to maybe xk bar, xn bar is fine, xn bar equal to a sequence xk, k equal to 1 to infinity, you have a n here, and x bar is something xk, k equal to 1 to infinity. So each xkn may converge to xk, okay, as n goes to infinity, but it need not converge in L1. Okay. That is clear because if you just take something xn, something plus some xk, okay, minus this xn. Say for example, if this xk goes to 0, okay, if xk goes to 0, xk minus xk plus xn minus xk, for example. If xn goes to 0, then pointwise it will go. But this xn is something fixed. If you sum it, it will be infinite. So there is no reason. Okay. The convergence here means L1 convergence means xn bar converges to xn. Xn bar converges to x bar is equivalent to saying summation mod of xk, xn k, xn k minus xn xk, k equal to 1 to infinity. Okay. And here you have the limit n going to infinity. The reason is you cannot take the limit inside. If xn k goes to xk as n goes to infinity for each k, that does not imply this sum, infinite sum that goes to infinite sum will be a function of n, right? So that need not go to 0. This should go to 0. I'm saying you have a sequence in sequence space. L1 is a sequence space. It contains sequence. So you have a sequence of sequences. Okay, that converges to one sequence of sequences, which is this, converges to this particular sequence. If this happens, you take the sum like this, which where you sum it over from k equal to 1 to infinity, then you take the limit n going to infinity, this should go to 0. Each of them may go to 0 pointwise. That's why it's pointwise conversion. Each of them, each entry may go to 0. Okay, which I just said, you can just add something in which goes to 0. That's enough. Okay, each of them may go to 0, but still the sum may not go to 0. That is equivalent to saying you have to take the limit inside. That is one condition which will ensure is if you have x and k is less than or equal to some yk, okay, such that summation mod yk, I mean, it's anyway positive, summation yk is less than infinity, then you can take the limit inside. This we have used in integral and other things in the last course itself. So it's a dominated convergence theorem. So you need dominated convergence to do this. Okay. So usually point-wise convergence will not imply the sequence will L1 converges. For that you need something more. Okay. Something should be dominated by a single sequence, which is a summable sequence. Same thing is for L2, and L infinity is just a supremum. It's uniform convergence. It's uniform in N. I mean, uniform in what? It is just a uniform in all those yeah, N, K, all this in the K, uniform in K, right? Okay, we will anyway discuss uniform convergence again with functions. Huh? Okay. Which one? I am saying that you have a sequence of sequences. For each N, it's a sequence. That's this is a sequence that will converge to this sequence. That means you need this sum goes to 0. This sum sequence of sequence is the sequence of sequence is indexed by N. When each sequence is indexed by K. Okay, then K equal to 1 to infinity. Okay, you have this. That limit N should go to 0. Hmm?
This like can be seen that they are like not finite and
Of course.
countable basis.
Countable basis means what? That's what there is no countable basis. No, there is no countable basis. We'll see, but in a different sense, there are bases. That's not the usual definition of basis. In a basis, it means that finite linear combination is dense there, which will not happen because of bare category theorem. Okay, but there will be something else, some other basis. Maybe with a different definition of basis is possible. Okay. Yeah. But you can have point-wise convergence. I mean, in a sequence. For example, if you define summation mod x xn by 2 power k, all bounded sequences. Xn is, I mean, all bounded sequences on L infinity or something. Xn is bounded. Then you can take this sequence. So that this will give point-wise convergence is equivalent to that. We will anyway see this again in something called Hilbert cube. Okay, how the topology looks and here the point-wise convergence is same as the convergence of the sequences. Okay. Summation x k equal to. You can take this norm and I mean you can define a metric like this. Okay. If you take two sequences xn yn, two bounded sequences, okay, then you can define a metric between them like this, and this will if point-wise if it converges, then that will work. Okay. This has to be k. This has to be k. We will come back to this again. Okay. Okay. Now we want to prove a very fundamental proposition or theorem about real line. Okay. We have defined real line as completion of rationals, but still we consider real line as the line. We can consider it like that because of total order in that. Okay. If anything here, either it should lie in the left side or right side because of the total order, and that makes sense. That's completely okay for our purpose. So if U is contained in R, with respect to the metric given by the modulus. Modulus gives rise to a metric here, which is like a norm. R itself is a vector space over R, and the modulus gives a norm. And with respect to that, there is a metric, and with respect to that metric, U is open is equivalent to saying U is disjoint union of intervals, okay? Possibly unbounded intervals. You have seen it. It was homework. It was homework. You should not have seen this. Okay. Okay. We will prove it anyway. Okay. This is clearly written as the syllabus part of this course. And I don't countable, yeah. The countable disjoint union. I mean, you said the countable disjoint union. Sorry. I mean, that is the point. Otherwise, it's always true. Countable. Okay, if you know the proof, can you tell me how to prove it? So other way is true, of course. If you have a countable disjoint union of open interval, that's open, that's clear, because union of any union of open set is open. So this way only we have to prove. So U contained in R is open, right? And how do we go? How do we go with the proof? Equivalence of what? Okay. So you want to go through that proof. Huh? Say it again. If x is equivalent to y, if open interval xy is contained in U, then okay, let's not go through that. There's a other way of doing it. Okay? So what I want to do is the following. So if we have a x in U, then of course there x is epsilon greater than 0, such that x minus epsilon, x plus epsilon is contained in U, of course, which is true. So there exists a open interval which contains x and which is contained in that. So I define Ax to be all those infimum of all those A. I mean, this can be infinity, minus infinity. This can be minus infinity, such that AB is contained in U and X is in U, AB. Okay, this makes sense. This set is not empty because there is a x minus epsilon, x plus epsilon is there. And you can take the infimum of all those A's. And this will give, this I define to be Ax for given any x. Any B, there exists B. B can be infinity. Okay, B is in infinity, A infinity. Okay. Unbounded. This could be minus infinity, and that B could be infinity. Okay, that's right. And you define Bx to be supremum of all those B, such that now Ax is defined, and Axb, there exists the Axb, okay, because B x plus epsilon will work as B. Okay, Axb contained in U and X is in Axb. Okay, so Ax and Bx make sense. Okay, we have taken the infimum, we have taken the supremum, and I call this interval Ix to be Ax Bx. And is it clear? This is contained in U. Should I go through the proof? It's very easy. I mean, this is for anything slightly above Ax. That interval is there. Okay, this is just says that Ax plus epsilon, Bx minus epsilon, or whatever. Okay, this says by this definition. Okay, this is contained in U for all epsilon. If you take the union, that is there. Okay, that's what the definition says, right? That's the definition of infimum and supremum. Okay, so if you take the union of that, that is just union of this is equal to Ax Bx, and that is contained in U. So Ax Bx is contained in U. Okay, we have defined an Ix, which is Ax Bx, and that is contained in U. Okay, now we make the following claim. That is claim is Ix either Ix is intersection Iy equal to empty for xy here. That is just the proof, just the quick proof of that the Ax is there contained in that. That's because for each epsilon that is true, because of that, which follows from the infimum supremum definition, and from that it is true. Okay, if you really want, go through the definition of infimum, what it means, or what supremum. It's a good exercise to write it down. Okay, it's better to do that. Okay, so supremum means, infimum means if you go slightly above, there will exist something below that, which will satisfy the property, and if you use that, that's what it means. Okay, so now Ix intersection Iy is empty, or Ix equal to Iy. This is the claim. Okay, I will not be. Okay, I will try to be as rigorous as possible, but intuitively it will all be clear for real line. Okay, if you want really kind of rigorous, you have to work with the Cauchy sequence as real numbers and all that with the total order. We will not do that. It will be clear for us for our purpose. Okay, So suppose you want to prove this. Suppose Ix intersection Iy is not equal to empty. Okay, not equal to empty. Then we want to prove Ix equal to Iy. That's what we want to prove. That is, we want to prove Ax equal to Ay, Bx equal to By. That's what we want to prove. Okay, and the first the claim of the subclaim is, in this case, okay, suppose we are assuming this, okay, we are assuming this, and we have to prove Ix equal to Iy. So we make another claim, which is this X is, of course, X and Y are in U. We have taken in U, of course, they are in U. I mean, only for things in U we define Ix and Iy, so they are in U. Okay, this closed interval is contained in U. Okay, of course, X is in U, Y is in U. We have assumed that. That's what we started with. So for any R less than Y greater than X, we want to prove that R is in U, arbitrary R between X and Y. We want to prove that is in U. And why is it true? So suppose not. We assume further. I mean, further assume and X is less than Y. Okay, I mean, either X is less than, they are not equal. If they are equal, there is nothing to prove. Ix equal to Ix. So they are not equal, and either X should be less than 1, Y, or Y should be less than X. So we assume X is less than Y. Okay. Suppose this R is not in U. We know that up to X to AY, BX. I mean, this is X to BX is contained in U, right? So this implies R is greater than BX. R is less than AY, right? If it is not there. Since closed interval what is it? X A X is contained in U, and this is B. A Y Y is also contained in U. Okay. So now, if suppose between X and Y, we are using, I mean, we are using our intuition as the real line something. Okay. If you have a R which is greater than X, less than Y, which is not in U, means it should be between Bx and AY, right? That is clear. Okay. You can argue with the definition also if you want. It is just messy, and you should do it privately. Okay. AY is defined. AY is corresponding to Y. Go on. One by one, let's go through. Yeah. So let me start. We started with X and Y. Okay. Or we started with X. We defined AX by that, BX by that. So for Y, there is a AY, BY. Okay. The claim is Ix is the interval AX, BX. The claim is Ix and Iy are either, intersection is either empty or they are same. That is the claim. So let's assume that claim, this is the claim. Okay. Either the intersection is empty or they are equal. Suppose the intersection is not empty, I claim that this xy, X is an element, Y is an element, this closed interval is contained in U. Of course, the endpoint X and Y are already in U. That's how we have assumed. So we have to prove that some R is greater than X, less than Y should be here. Suppose not. Okay, suppose not. We, by definition, X, BX is contained in U. For a given X, you have AX, BX. Okay, X is here. For given X, you got an interval by taking infimum, supremum. Okay, that's how we defined AX and BX. So this is contained in that. Okay, so now X is here. So X to BX is already in U, and AY to Y is already here. So if R is not in U, means it should be between AX and AY, right? Okay, so that is what I have written. If R is not in U, suppose not, that is R is not in U. Okay, suppose not means that is R is not in U. Okay, that means R should be greater than BX and less than AY, right? That's clear. Okay, then what is the contradiction? Yeah, that means they don't intersect. That's all. That means they don't intersect. Okay, this implies Ix intersection Iy is empty, which we have assumed, which is not true. That's all. No, no, Ix intersection Iy is empty. Ix equal to Iy. Where is it coming? It is greater than Ax means Ax, Bx is here and some R is here. Then Ay, By is here. They are just distant. This R is separating those two. Okay? Ix in intersection Iy is empty. That's what it means, right? So, which is contrary to our assumption. Okay, hence the claim, hence the subclaim, which is the whole interval xy is contained in U. So explain what? No, Ax Bx is Ix. Ax Bx is Ix. R is greater means R is somewhere here in the number line. Ay By is Iy. R is somewhere here. So this means these two are disjoint, right? There is some R which is, by definition, the whole interval is there. This Ax is defined by so that the whole interval is there. Okay? Correct. Okay. So we have proved. So we have proved that this xy is contained in. Now we have to prove that Ax is same as Ay, Bx is same as By. That's what we have to prove. Okay. Now in general, if x is less than y, then Ax is less than Ay, less than or equal to Ay, right? By definition. Ax, where is the definition of Ax? Ax is the infimum over this. Okay. So is it clear from the definition that if x is less than y, x is, you have to prove that if x is less than y, then you can, I mean, this any AB containing y, okay, that A will work for this also. Okay. I mean, that may not work. If it is outside, it will not work. But if it is inside, it will work. If x is inside that, you have to see to consider two cases. Anyway, leave this as an exercise for you. Okay. If x is less than y, this is exercise. What is the exercise? If x is less than y, Ax is less than Ay. That's because Ay is the infimum of some A in the interval. Okay. If x is in one of those interval, then by definition of the infimum, Ax is less than Ay. Otherwise, it will be x is less than y, so it has to be, I mean, in the left side of this, so this should be true. Okay. Okay. So Ax is less than Ay. So, okay. So now for this case, in this case, okay, this is anyway true. So Ax, so we only need to prove, I mean, in this condition, only need to prove Ay is less than or equal to Ax, right? That's what we have to prove. To prove Ax equal to Ay. I mean, we are assuming this. See, remember, we are starting with this claim. Ix intersection Iy is empty. We start with this. Then we proved a subclaim that this closed interval is contained in U. Okay. From this, we want to conclude that Ax equal to Ay. This is anyway true. X is less than y, that is true. Okay. Now we want to prove Ay is less than Ax using this condition. Okay. And let me orally say this and write it there. Okay. So now, okay. Okay. Now Ay is less than Ax. That's what we want to prove. So now we have that. Okay. So now if AB, yeah, Ay is less than this. If x contained in AB, x is in AB, is contained in U. Okay. 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 Then A y, Ay, for example. Okay. This is also contained in U, right? Because x is here and x to y is also there. So this is also contained in this. So because it's open, there exists some y plus epsilon is contained in U. because it's open. Okay. Now for any x is like this and y is inside this. Okay. And this is just the infimum of all those things. So this implies ay is less than or equal to ax by definition. Some a works for x. Okay. The same a will work for y also. And you are taking the infimum. So ay should be less than ax by definition of infimum. Okay. Is okay. So these things implies ax equal to ay. And you just have to reverse the argument. Similarly, ay bx equal to by, okay, which is ix equal to iy. If ix intersection iy is not equal to empty, so this just says either they are different or they are equal. Okay, either they are disjoint or they are equal. Okay, that's what this says. Now, of course, any u is union of all those. I mean, it's just union of all those things. U is equal to union of ix, where x is in u. Okay, which is always true. Everything contains x. But then you define an equivalence relation. X is equivalent to y if ix equal to iy. Okay. Then you define u is equal to disjoint union of equivalence class x, and you take a single ix. This is a disjoint union. Okay. We are I mean, from this equivalence class, we are taking only one. Okay. And if you want, you can write equivalence. I mean, you can write an equivalence class of this if you want. Ix. Okay. Then this is a disjoint union, because when they are in different equivalence class, they are disjoint. So this is a disjoint union. So any open set is disjoint union of intervals. Now you choose a rational number from that. If rational number is dense, which we haven't proved, but you will prove it in the assignment. I have to post it. Okay. And I will post it. I mean, I will, with the other problems, I will post it in this weekend, surely. Okay. So now choose Ux in Ix. Okay. Then U is equal to integral of x vector I dx, if you want. And this has to be countable because rational numbers are countable, and that's all. The countable union of, okay, it's done. Any problem? Any comment? So that someone was, you are saying about equivalence relation something, no? That is in Rudin, right? Is it in Rudin? Huh? Same proof, this proof. Sure. Okay, yeah. Yeah, I think in comparison book is also exercise, but it follows this, I think. I'm not sure. Okay, so next I want to discuss continuity, which you might have seen. So shall I go through fast, or we will go through the proof if you want, if someone wants. If anybody wants, please tell me. Okay, since you say you have gone through it, I will go. So definition, you have a function from x1 to x, maybe you take the metric page, x1, I mean, it is just a function from x1 to x2. To denote the metric, I write it x2 d2, okay, is continuous. Same definition. You can take any definition like sequences or open ball or something. But here we use this definition. If continuous at some point x0, if, oh no, it's in WhatsApp. I'm sorry. I have WhatsApp there also. Here it is in silent mode, so they are calling me there. Sorry. So this is continuous at x0. Okay. If for given epsilon, for given epsilon greater than 0, there exists a delta greater than 0. So this delta will depend on the epsilon such that for all x in, I mean, x in, yeah, I mean, d of x naught less than delta will imply d of f of, I mean, this is d1, this is d2, f of x naught, f of x is less than epsilon. Okay. Yeah, you're saying something? This is equivalent to saying x is in b of x naught delta implies b of, I mean, this is with respect to b d1 and this is with respect to b d2, f of x naught epsilon. Okay. I mean, this just says that then f of x is here, which is equivalent to saying f of b of x naught delta given epsilon, given x naught, given epsilon, there exists delta such that f of this is contained in b of f of x naught epsilon. Okay. From here, from this statement, it's easy to derive this. I mean, inverse image of open set is open and all that. Okay. Okay. Here, f of x is here. Open ball, f of x naught epsilon, f of x is here. X is here, this implies f of x is here. This is the same statement here. Okay. So now the proposition to tell me the proof. Okay. F is continuous at x naught. Okay. The following are equivalent. First one, 2. So u, if f of x naught is in, f is continuous, f of x naught is in some u, then f inverse of u, which is a set, it contains f inverse u is open, that's all. It will contain x naught, of course, right? And it is correctly, no? Yeah. Then the third one is, what else? Yeah, I mean, you can reframe it in different ways if you want, using open bar and other things. So if xn converges to x, then f x naught, then f of xn converges to f of x naught. Okay. So shall I write the proof, or it's you already know it? You know it. Okay. So I will go through the argument. That's all. Okay. So f is continuous at x naught. So this means this is contained here. Okay. Now if you have an open ball around here, if you have an open, so you want to prove 1 implies 2. You want to prove 1 implies 2. So the 2 is basically if you have an open set which has where f of x naught is an element of this. That means there exists an epsilon such that f of x naught epsilon is contained here. So that means there exists a delta such that this happens. Okay, and from that it will follow that, I mean, from but then f inverse of that will, I mean, there will be a delta such, I mean, x naught delta which is contained in there, that will imply that x naught delta is contained in f inverse u. That will imply f inverse u is open. Okay, given epsilon, there exists a delta, so that if you have a u which is open which contains f of x naught, then there is a epsilon ball around this which is contained here. You take the inverse image of, I mean, you take I mean, from the definition of continuity, there exists a delta such that the open ball, delta ball around x naught, okay, satisfies this relation, which exactly mean that x naught delta, the open ball x naught delta is contained in f inverse u, which means f inverse u is open. Okay. Now you want to prove that this condition. That is just if xn converges to x naught, you want to prove this goes to this goes to this. Okay. Now you given epsilon, you want to, so you want to prove this only basically. Assuming this, you want to prove this. Eh? That is later. We have to prove 2 implies 3, no? How do you, instead of this, you cannot prove that. We are proving 2 implies 3. So 2 implies 3, assuming this, you want to prove this. Okay. So xn converges to x naught, then you want to prove this. So you assume this and you want to prove this. Okay. That is given epsilon, you want to prove a epsilon ball around this where everything is contained here after some time. Okay. Yeah, yeah. U has to be open. F of x naught contained in this, U is open, right? Then Inverse image of open is open. Maybe I didn't write. Okay. So similarly, if xn converges to x naught, you want to prove this. So now you want to prove this means if you take a ball around this f of x naught, epsilon ball around this, you want to contain all this sequence after some time. So, but given epsilon, you have a delta such that all these things are contained after some time. But then from this condition, it will prove that those things are contained in there. So this is clear. Now this is true for all xn. Okay. Now this should imply f is continuous. That definition has to satisfy. So it's easy to prove prove by contradiction. Suppose f is not continuous, you can produce a sequence such that this does not happen. F is not continuous means what? There exists an epsilon naught. There exists a single epsilon naught, constant epsilon naught, such that for all delta, okay, for all delta you can take it to be 1 by n. For all delta, this condition is not satisfied. So for all delta means you take delta equal to 1 by n. This condition is not satisfied means this is not contained in here. So there will exist something which is here, which is not here. Okay, you take that as xn. Okay, that xn, because it is in this, it will goes to x naught, but the f of xn will not go to here. So is the proof clear, or you want me to write it? I hope you don't want me to write it. Anybody want me to write? No, it's okay. Okay, so I assume it's it. So that's all about continuity. And we say f is continuous on x if it is continuous at every point, and f is uniformly continuous if you can choose the delta uniformly for all x. Okay, I mean it should depend on epsilon, of course. So if you can choose it for this. Now the crucial question comes. So x is a metric space, any metric space. How do you know there are continuous functions on that? Okay, can you give me a continuous function on this, any metric space? Apart from constant function, non-constant function. Okay, I want to answer this question. You take xy in x and x is not equal to y. Then does there exist a function f such that f of x is not equal to f of y? Okay. This is what it means that the functions are much larger than the space. X is a space. This means each point can be separated by a function. This is not a function, this is a continuous function. Okay. Continuous f. I mean, any function will be always there. Okay. Continuous function, constant function will not separate anything. Okay. This is what is called separating the points of x. So, are there continuous function which separates the point of x? So, that is the question. Now, given 2x and y, x is not equal to y, does there exist a continuous function such that f of x is not equal to f of y? So, it cannot be constant. So, are there enough functions, enough continuous functions on a metric space? X and y? Yeah, x is not equal to y. Yeah.
Metric is a continuous.
Yeah. Yeah. Exactly. Distance between them. But how will you define that? You can take, that's what. So we get continuous function from the metric itself. So that's what we get. So if you want, you can do this. If you want x cross x on x cross x, you can define different metric. And you can define, for example, d1 of any xy, x1, y1, x2, y2. Okay. You can define it to be summation d of x1, x2 plus d of y1, y2. Okay. Or you can take the square of this, take the square root of that, you call it d2. Or you take the maximum of this, you call this d infinity, whatever. Okay. You can define a metric on x cross x. So you have so x cross x is also a metric space. Okay. Then the conclusion is, this is just a remark. I will not write the proof. Okay. Remark is d is continuous. D is a function from x cross x to real line, right? Is continuous with respect to that metric. Okay. So with respect to this metric, something is continuous. I mean, with respect to this metric, which is a metric on x cross x, some sequence sequence of tuple, okay, which converges here, if and only if it converges coordinate wise, right? Which is same, which we have already seen. Some xn, yn converges to xy. If xn converges to x, yn converges to y. That is clear from this, which we have already seen in Rn and other things we have seen. So because of that, it will follow. If xn converges to x, yn converges to y, then d of xn that will converge. You just have to, I mean, anyway, we can just write it. It just, of course, there is nothing else we have. We have only triangle inequality. we just have to use it. We only have triangle inequality, nothing else. So we have to use it. We want to prove that D is continuous, so we have to prove that D of xn, yn minus D of xy. Okay, if xn converges to x, yn converges to y, which is equivalent to saying xn, yn, that tuple converges to xy. Okay, so if this happens, then we want to show that this goes to 0. Okay, now yeah, this is less than or equal to triangle inequality xn, xn, yn. You can just add few things, right? Plus, I mean, this is equal to D of xn, yn minus D of x, yn plus D of x, yn minus D of xy. Okay. So now this is, now again use triangle inequality. So this modulus plus this modulus. Okay, I'm just following that step. And this is just less than D of, you just have yn in common, so x and x plus D of x in common, so y and y. It is just triangle inequality. There is no real complex real valued function is also complex valued function. Real valued function is a complex valued function also. Fx equal to x is not it's on metric. No, I'm talking about real valued complex valued. Yeah, correct. That's what your question would. Yeah. So a metric is continuous. Now you define, now for x not equal to y, okay, define fy equal to, fy is a function which depends on this, fy at x equal to d of xy. Okay, then this function satisfies fy of y equals 0, which is not equal to dxy, which is fy of x. Okay, so you have got continuous function which separates the point x and y. So continuous function separates. If you have a metric space, then you have continuous function separates. If you want bounded function, then use that d by 1 by 1 plus d. You can use that if you want. If you want bounded continuous function to satisfy, we will come to that. Come to that later. Okay. This, there is nothing like all continuous. Constant function will not separate, for example. Are there continuous function which separates any 2 points? That is the question. You have, see, the point is you have separate points means you have a collection of functions. That collection of functions separates points of a set of where it is defined. If for any given point, you will have different values for that. That's what the definition of separating points.
Are you interested in this such functions if they're like larger or?
Exactly. This is something like where do you have enough functions? In normed linear space, you will have enough normed. I mean, if you have a normed linear space, whether you have linear function which separates that, that's the question. That will be answered by some theorem. So this is a basic question. Okay. And it is not just continuous, it's uniformly continuous. So you have proposition. You have a set A contained in X. Of course, X is a metric space and all that. Okay. Then dA X, which we have already defined, infimum of all those A, such that dAx. I mean, infimum of dAx, right? dAx, such that A in A. Yeah. Sorry. Okay. This is a minimum distance, infimum distance from a set to this. This function is uniformly continuous. It's continuous. I'm saying it's uniformly continuous. I mean, we have to prove it's continuous. Okay. We have proved that metric is continuous. This is slightly more than that. Okay. Huh? A is a fixed set. There is no closeness. A is just set. Okay. A is some set. Okay. For any set, dAx, dA is a function. dA is a function from x to 0. Okay. If x is in A, it is 0. This function is uniformly continuous. Okay. So to prove uniformly continuous, enough to prove this. I mean, this is not a equivalent condition, but this condition will imply uniform continuity. If you have any 2 functions, I mean, if you prove this, for example, f of x minus f of y is less than or equal to c times x minus y. Whatever. I mean, this is for real line. So we need this dA of x minus dA of y, okay, is less than or equal to d of xy. Okay. If we prove that, that proves uniform continuity, right? Uniform continuity, what given epsilon, you have to find a delta without any, I mean, without referring to that x. Okay, which should, the delta should be same for x and y. Okay. Now d of x, this is true for anything. If you take any epsilon, then take that delta to be equal to epsilon itself, right? You can take it to be equal to epsilon. That will work. Okay. So this works for everything. So we have to prove this. But we cannot prove here because there is an infimum here. This is real number. Okay, so I am putting modulus here, and this is d of xy. So here there is an infimum, here there is an infimum. I mean, just to get the idea how to prove it. We cannot prove it, just two infimums are there, and I mean, their difference, we cannot get any reasonable inequality. So to do that, let us do this. D of ax. I mean, anything, any basic thing, basic inequality, any basic equation or inequality on metric, we have to get it from triangle inequality. Okay, there is nothing else we have. So we write that, okay, which is less than or equal to d of ay plus d of xy. Okay, we have this for all a. X and y are fixed. Okay, this is true. So this is true for all a. Okay, so now this is greater than or equal to dA of x, because that is the infimum. This is true for all a. So this is greater than or equal to this. This is right. So now we have this inequality dAx. I mean, it is better to write these steps, is less than or equal to dAy plus dxy. There is no small a here. This is just a number depending on x. Okay, and here a is varying. Now you take the infimum here, and this has no role. There is no a here. Now you can take the infimum. That is how you should take. I mean, you have this inequality, doesn't mean you can take infimum here, which is what I'm finally doing, essentially doing. But the point is, you have to first take this. This is the argument is this. This is greater than this for all a, so this inequality follows. Now here there is no small a or something. This is just a constant, single constant, where this is true for all a. Okay. Now you can take the infimum over this. Something is greater than something for all a, then the infimum over this will also be greater than this. Okay. By taking infimum, that just implies dAx is less than or equal to dAy plus dxy, right? I didn't write the argument. Now you can take the infimum over here for all a and you get this. Okay. This is how you should get. So this implies, of course, dAx minus dAy is less than or equal to dxy for all xy. Okay. Now there is nothing to do with x and y. You can interchange xy. This doesn't change. So that will just become a minus sign. So you can put this by interchanging x and y. Okay. Okay. So we have got the inequality. So it's uniformly continuous. Okay. So if you have so now the definition, you have a x and you have a topological space. This is a collection of open sets on this. Okay, a topological space is Hausdorff, the German mathematician, Hausdorff, if any 2 point can be separated by open set. That is, if x and y in x not equal to y, then there exists ux which has x and uy which has y open sets. Okay, I mean, open sets means they are in ux, uy in that topological space. Okay, such that ux intersection uy equal to empty. If you have 2 points, then there are open sets around that point which are disjoint. Okay, this is what is called a Hausdorff property of a topological space. Okay, and it's easy to see that any metric space is Hausdorff. That's what we want to prove, and that is clear, I believe. Hausdorff property is equivalent to saying the limit of sequence is unique. That is also clear. Okay. I will just here x comma y, x not equal to y, x not equal to y. I mean, they have to be different, no? Of course, in metric space, if x not equal to y, then you take delta to be delta less than d xy by 2. And of course, bx delta intersection by delta, these are open balls equal to empty, right? So it follows. So any metric space is a Hausdorff topological space. Okay. Okay. So this statement is same as the following statement, except that here they are singleton x and y. I will write the following statement. The next definition: a topological space x tau is said to be normal if A B contained in X closed sets such that A intersection B is empty. We have two disjoint closed sets in a topological space. Okay. Then there exist UV open sets. Okay. It's in the topological space, means it's open set. I mean, with respect to the topological space, this is not need not be a metric space. Okay. It is just a collection of sets which satisfy some axioms. Okay. Such that A contains U and B contains V and U intersection V is empty. You have two disjoint closed sets, then there exist two disjoint open sets containing A and B. That's all. This is what is called normal property of a topological space. Hausdorff is you just instead of A and B use singleton X, singleton Y. That's all. Huh? It is just a collection. Topological space comes with a collection. Anything in tau is open. I defined in the last class. Huh? Say it again. Close is complement of open. Yeah. Or you can use define through limit point also. That will work. Same definition will work there. Any UN open in tau means open. It is open. Huh? There exists U. There, this is there exists. Such that. It's strange that you haven't seen it. Nobody told me, only in this class, I hear someone saying that they haven't seen this notation, such that. Huh? Yeah, last year, that's what I'm saying. Before that, nobody asked me in 20 years. So first time I'm hearing someone saying that they haven't seen this. Yeah. They are not educated. Okay. So we want to prove this. Okay. The proposition is a metric space is a normal topological space. Okay. Metric space is normal. Okay. So that is a property. That's the definition is for any topological space. You have a topological space. You have X. You have a collection of sets declared to be open sets. Then the topological space is said to be normal if it satisfies that condition. Given any two disjoint closed set is contained in open set which are disjoint. Okay. Here we want to do this proof for any X. So suppose A and B are contained in X closed. A intersection B is empty. You want to find Ux and Ub. Okay. You can directly define. So we have already proved that inverse image of open set is open, which is equivalent to saying for a continuous function. So for inverse image of closed set is closed for a continuous function. Okay. So from that it will follow. So now dA and dB are continuous function. Okay. So let us define f of x. F is equal to dA by dA plus dB. And before that I need a lemma, small lemma. Maybe I will write it here. There. I will write. I'll just come back. This is a lemma or something, which is very easy. A is contained in X, then dA X equal to 0 is equivalent to saying X is in A closure. It's easy, clear? Of course, dA. Okay, by definition. Exercise is okay, no? If dA X equal to 0, then there exists a sequence Xn in A which is so X is in A closure. Similarly, if it is there, then from yeah, exercise. Okay, this is done. Huh? Exercise. No, not such. Okay. And also, so this is true. Also, so if it is, if I mean, this is for any A. If I mean, so X is dA X is 0 if and only if X is in A closure. So if A, B are closed and disjoint, then dA plus dB is never 0. Okay, for all X. Okay, this is never 0 because if it is 0, it has to be in one of them. If this is 0, if it is in A, this is 0 if it is B, it cannot be in A intersection B because that's empty. Okay, so they are disjoint, so they're never 0. So you can, this is never 0. Okay, so you can define this now dA by this. Okay, so now it's clear f of x equal to 0 if x is in A. F of x equal to 1, right? See, if x is in B, this will become 0, dA by dA is 1 if x is in B. Okay, and it is between, now f is from x to interval 0, 1. Okay, 0, 1. And let's take u equal to f inverse of 0 half, which is open set, and v is equal to f inverse of half u, which is, this is an open set, right? This is open set, nobody has a confusion over it. In 0, 1, this is open set. Okay? Don't ask, this is closed interval, you don't have this question again. Okay? This is open set, this is open set, they are disjoint. 1 by 2, 1, right? 1 by 2, 1. Okay, they are disjoint, and this is u, this is v, they are open, and that contains this. Okay, so this work. Okay. I want to do something more, but maybe I'll stop.